Alright, let's do some more Spivak exercises. Okay, so let's hear. So we're talking about limits here. So we want to prove this thing. Okay, so let's see here. So I claim, and basically the first thing we're going to do is we're going to rewrite what we're trying to show here, these limit things. So what we want is that for all epsilon greater than 0, there exists a delta greater than 0 such that the norm of f of x minus b is less than epsilon. This inequality holds for every single x in b delta a. And what this is this is the set of all x such that x minus a is less than delta. This is the ball of radius delta centered at a. It's just the shorthand that I use. I sort of prefer this over the over this notation. It's more it's easier to write, and it's like, oh, you've got this b here, and it's b for ball. So there you go. Okay. Oh, I haven't finished this sentence. I claim this holds if and only if for every single I equals 1 through m, then for each of these i's, for every epsilon, there exists a delta. And of course, this is epsilon greater than 0, delta greater than 0. Fi of x is minus bi in norm is less than epsilon for all x in b delta a. Okay, so we'll start with the backwards direction. So we want to... So in this backwards direction, we know that this thing holds for every single I. And so what we want to start out with is... We want to start out with an epsilon greater than 0, and then we want to exhibit a delta greater than 0, which does this stuff. Let's see here. Because we're going in the backwards direction, we're assuming this second statement. And so we know that for every single index I, there exists a delta I greater than 0 such that Fix minus bi is going to be less than epsilon over n. Now we're going to let delta be the minimum of delta 1 through delta n. And because we've chosen finitely many deltas here, delta i's, because there's finitely many of them, this number is going to be some number greater than 0. Alright, so then what do we have? Then for all x in... Let's see here. Let's do this one step at a time. I'm going to include this. Then the ball of radius delta centered at x is going to be contained in the ball of radius delta I centered at x for all I. So then for every single x in this ball of... No, it's these balls are centered at A. Okay, so then for every single x in this delta ball, we have... What's the difference between f of x and b? Well, remember, this is... in this textbook, we're only using the Euclidean norm. A lot of these things will hold for... A lot of these statements you can generalize to general norms, but that's something where you would want to read through, like, Baby Rudin or even Folland to learn about that stuff, which you totally should do because that stuff is so awesome. But anyways, so we have we're just rewriting this f of x minus b, since these are elements in Rm, we can write it component-wise. So here, these should be m's. I wrote n in my when I wrote up this solution, so I might make that mistake. If I ever write an n, I mean m. Okay, looks good. So this is equal to this, but remember, this is, I believe this is problem 1-1, that this norm is less than or equal to the sum of the norms of the individual entries. So this is going to be less than the sum from I equals 1 to m of fi of x minus bi. And now since this delta ball is contained in every delta eyeball, we can replace every single one of these with this, because we've satisfied the condition that we had from before. So this must be less than, or, well, actually strictly less than, the sum from I equals 1 to m of epsilon over m. And that's just going to be exactly epsilon. Okay, so what have we proven? We've proven that given any epsilon, we've proven that given any epsilon, we can choose a delta such that for every x in this delta ball, the difference between f of x and b is less than epsilon. Thus, f is continuous at a. Yeah. So that's all we need for the backwards direction. All right. So now let's move on. We will prove the forwards direction contrapositively. Now, you might be able to prove this, you probably can prove this directly. I mean, at this level, of course, most of the things that you want to be true are true, so you probably can prove it directly. This is just the quickest argument that I came up with. And also, there is some, like, logicians can sort of get fussy about this, about proofs by contradiction. There are logicians who don't believe in doing proofs by contradiction, and furthermore, in general, in proofs, if you have the option between proving something directly and by contradiction, you want to go with proving it directly, because typically proving it directly, the proofs will look neater, and they will also give you a little more insight into what's really going on. But contrapositively, when we say contrapositive, what we're doing is typically if you have a statement A implies B, this is logically equivalent to not B implies not A. So we're not actually doing contradiction here. We're just proving a different statement. We're assuming not B and proving not A, and that is logically equivalent to A implies B. Okay, so my proof that I had written down here was actually wrong, so I had to take a little bit of time to fix it. But now we're good. So we're going to prove the forwards direction contrapositively. So suppose not every fi is continuous at a. Okay, so if it's continuous, if every single fi is continuous at a, then that means that for every single fi, for every epsilon, there exists a delta such that the norm of the differences is bounded above by epsilon for every single x in a delta ball. So if that's not the case, that means that there must exist an I and there must exist an epsilon such that no matter what delta you choose, there will always be a point in that delta ball such that the difference between f of x and b is greater than or equal to epsilon. That's what it means for this is equivalent to it not being the case that fi is continuous at every single a. And this is a sort of thing like we've got all of these like there exists and for all in here, and like if you're not super comfortable with proofs, or if you're just getting into proofs, it can be really difficult to keep these straight in your head. But my advice is to just sort of keep working through problems like this, and you sort of will get the hang of it. At least that's sort of how it worked for me. Now this is sort of it's gotten to a point where this is sort of second nature for me. To be able to say like, oh, how do you logically phrase the logical opposite of a statement involving a bunch of like logical operators. But anyways, okay, so we suppose there exists an I and an epsilon such that no matter what delta you choose, for any there is going to be a point in that delta ball which gives you this inequality. So what does that mean in terms of what we're trying to prove? So for this choice of epsilon, then for all delta greater than 0, there exists an x in b delta a for all delta greater than 0, if we choose x in b delta a such that these should be fi, bi, such that fi of x minus bi is greater than or equal to epsilon, then what do we know about the difference between f of x and b? Well, remember, this is just the norm of the coordinate. So if you were to write this out, this would look like you take the sum from I equals 1 to m of, so you take each fi x minus bi and you square it and you take the square root. So you're taking the sum of a bunch of positive numbers here and then taking the square root. So this is going to be bigger than just throwing out a bunch of these positive terms. So, okay, well I should use j here so that we don't confuse it with the I that we've chosen, because we've already chosen, I already means something in this part of the proof. I specifically refers to this this index such that fi is not continuous at a. Okay, so this is equal to this. Well, this is going to be greater than or equal to just if we take that particular fi of x minus bi, and we square this and take the square root of this. Okay, so this is just fix minus bi. But by our choice of epsilon, delta, and x, this is going to be greater than or equal to epsilon. Okay, so what have we chosen? So there exists an epsilon such that for all delta we can find an x such that f of x minus b is greater than or equal to epsilon. this means that f is not continuous at A. So what have we proven? We've proven that if not every fi is continuous at A, then f is not continuous at A. And what's the contrapositive of this statement? Contrapositively, if f is continuous at A, then it is not the case that not every fi is continuous at A, i.e., then every fi is continuous at A. And that's exactly the direction that we're trying to prove. And so this means that we're done with the proof. So, yeah, there you go. That's it.